Okay, class has started. Dan.
Sorry.
I liked it better when you used to sit over there. Oh, man. I don't feel like it. Okay, so we've been talking about internal loads, and last time I talked about using rotation matrices to re-express the external loads on members so that you could do internal loads calculations. So here was the example that we did. No, that's missing the whole point. We had a cantilever beam at an angle of 30 degrees with a length of 0.2 meters and a downward force of 6,000 newtons. And we want to calculate the internal loads. And we first calculated the external loads. So we got something like this. 6,000, and then there was a couple at the wall of 1039.23. And then we use rotation matrices, a rotation matrix to re-express each of these loads. The couple doesn't change because that's a z component, and we're doing this rotation about z. But we went from this to this, and that was a negative 30 degree angle. So our rotation matrix was equal to 0.866, negative 0.50, positive 0.5, positive 0.8660001. And so we got this. So this represents our new coordinate directions. Those vectors are negative 3,000, 5196.15, and then this is opposite of that. And then we had this unchanged couple of 1039.23. And once you have it in this coordinate system, mathematically, I mean, we don't care how we look at it. So going from this to thinking about it like this is the mathematical equivalent of turning your head a little. So this is what we have now. Negative 3,000, positive 5196.23. The couple, 1039.23. No, that would not affect the problem at all, but I have the wrong decimal here. That should be 0.15. And then over here, equal and opposite, so positive 3,000, negative 5196.15. And now we're ready to do the internal loads for that. So how many places are there where the subfunctions are going to change? 2, just the endpoints. So one there, and so how many cuts are we going to do? Just one? So that's valid for all x's from 0 to 0.2. So over here we have negative 3,000, positive 5196.15, a couple of 1,039.23, and then tension, shear force, bending moment, and we don't have anything producing torques about the x-axis, so I'll just leave that off. But now we can calculate the internal loads. Newton's second law says negative 3,000, positive 5196.15, plus T negative V is equal to zeros. So T is equal to positive 3,000. And V is equal to positive 5196.15. And then the moment equation calculated about that left endpoint. The force vector at the left endpoint doesn't produce a moment about the left endpoint. We do add the couple, and then we have plus m minus vx is equal to 0. So m is equal to vx minus 1039.23. And so m is equal to 5196.15 times x minus 1039.23. And so with that approach, you can do it for, you can do this for any structures too, because the only difficulty of doing it with structures is once you calculate those external loads, your coordinate system isn't automatically rotated the way that you want it for internal loads. Let's do those 6 checks.
Are we supposed to be writing 6 checks if we're going to be like asked to check it? Or can we just do it mentally?
I think it is, normally you can just do it mentally, but I might ask questions about it, and then you must do it in written form for me to grade it.
Is this considered a structure, this one?
No, not really, but it's just one where it's just the shortest example I could come up with where the coordinate system was not oriented along the beam's axis. Otherwise, we would have had to go through another structure calculation.
What if our coordinate system would be rotating?
Was what?
Accelerating.
Yeah. You don't want to do these problems in non-inertial coordinate systems.
Let's not.
Yeah.
Just asking.
So if you were doing a structure, then each member you might rotate a different.
Yes, exactly. Each member would have a different rotation matrix in general. That's right.
What if it's
Yeah.
not inertial?
Well, actually, since deform, we're not dealing with any time dependence. We're doing everything instant by instant. All you would have to do is,
Break the movement into instant by instant.
yeah, you don't have to worry about the stuff that we're worrying about in dynamics. You just have to instant by instant, whatever that rotating coordinate system is, at that instant you need a rotation matrix to re-express it. So it wouldn't be as complicated as dynamics because we're not worried about the time dependence.
What if you were worried about the time dependence?
Well, that's a good question. Okay, so with elasticity, there is no time dependence. Unless, so everything happens instantaneously in elasticity. You apply the forces, there's an instantaneous deformation that occurs. And so there's really no natural time dependence in any kind of elasticity problem. By the way, that means that that elasticity can't be, that this, you know, before you even look into it, that this is only approximations, because there can't be any such thing as instantaneous signal transmission, and that's what this says there is. You apply a force, there's an instantaneous change to the deformations, you know what I mean? So, what were we talking about? Not relative, not special relativity, but that's so. Yeah. Okay, so the 6 checks. The first one, take the derivative of m with respect to x. That should be equal to v. That holds. Second one, take the x derivative of v with respect to x. That should be equal to negative q. dv dx is equal to 0. There's no distributed load, so that holds. Okay. Third, the tension at the endpoints. Is there a horizontal point force at the left endpoint? Yes. At the right endpoint? Yes. So tension needs to be non-zero at both endpoints, and that's what we got. Is there a vertical point force at the left endpoint? Yep. Right endpoint? Yep. And so those should both be non-zero, and that's what we got. Is there a point couple about the z-axis at the left endpoint? How about the right endpoint? No, you got lulled into complacency. So there is a couple at the left, but not at the right. So we should have non-zero m at x equals 0, 0 m at x equals 0.2. And so it's non-zero at x equals 0, so that's good. Plug in. So hopefully 1039 is 1/5 of 5196. It looks like that roughly checks out too. This is shorthand for t is equal to 0 if and only if there are no horizontal point loads at that endpoint. T equals 0 at an endpoint. If and only if. Okay, so that's why I wrote that shorthand, because it's very tedious to write. But that's what it means. And same thing with v equals 0. Same thing with m equals 0. And then the last one is the torque about the x-axis. That doesn't even come up in this problem. So there's no point torques at either end, and there's no internal torque anywhere, so that one checks out. Okay. Any questions about that? So yeah, what Travis asked, in a structure, you'll have a different Q matrix for each member. So, what? No. Okay, so if you have a structure like this, you'd calculate the external loads, and then for this member, Q takes this coordinate system to this coordinate system. And for this member, I mean, you always have two options, but this one would go from this coordinate system to either this coordinate system or the one at 180 from this.
Isn't that a little q? That's the slope of the distributed load? Is that what it would be?
The little q is a downward distributed load function. So like if you have okay, so if this is 2 meters and this is your distributed load, say this is 10,000 newtons per meter. That line is defined by a rise of 10,000 over 2, so 5,000x plus 0, because there's no y-intercept. And so Q is equal to 5,000x. No, that's the wrong Q. What's Q? Yes. Okay. Any other questions? All right, so now we're capable of calculating the internal loads and beams, and we're finally going to get to using those internal loads to calculate stresses, so that we'll be able to calculate the stresses at any point in a beam. So now that we can calculate internal loads, we're going to use them to calculate stresses. And so the way we're going to do this is just as vector components add, tensor elements add. So for example, 5, 0, 2, 0, 1, 0, 0, 1, 0. Let's make it symmetric. Plus 0, 0, 0, 0, negative 4, 0, 0, 0, negative 3. So how do you add those two stress tensors? You just add them up element by element. So that would be 5, 0, 2, 0, negative 3, 1, 0, 1, negative 3. And in a beam, the total stress tensor is equal to the stress tensor due to tension plus the stress tensor due to the bending moment plus the stress tensor due to the shear force plus the stress tensor due to torque. And we're going to have formulas, ways of calculating each one of these four things. And so we're going to calculate those independently and then add them all up at the end. One thing to keep in mind, notice that this ability to calculating the stress total by calculating the stress for each individual internal load and adding is only possible because we're dealing with small deformations. So, in fact, if you had large deformations and you did like a finite element calculation of these four things, you wouldn't be able to just add them up and get an accurate estimate of the total stress. But we can do it because of these small deformations, and so superposition applies. That's what this is called, superposition. It's a good name. So we're going to go through each of these four things. So first, stresses, this is the easy one. Stresses due to tension and compression. So I'll follow this along with an example. Let's say that we have 8,000, and then over here we have 2,000 at the center and 6,000 at the end. And let's say that this bar's cross-section is 0.001 meters squared. Okay, so at any point in the beam, sigma xx, and we're using this coordinate system, sigma xx is equal to the internal tension divided by the cross-sectional area. That's not really a surprise because that's exactly how we calculated stress when we had uniaxial loads applied to a member that was loaded like a stress element.
So that would be traction.
What?
Wasn't that the traction vector before?
The traction vector is kind of like, well, that's the distributed load, or that's the force per area applied to a face or applied to a surface. That's not the same thing as this T. This is the internal tension. So this is what you calculate from the internal load, process. Okay, so let's figure out with this example beam, what's the stress tensor due to tension for points along the green dotted line?
Really?
Sucker. Yeah, insert whatever color you want there. You could make it paisley or something. I don't know. That's not my problem.
Fine.
Yeah. Anybody need time to go to the bookstore real quick?
There still is.
There you go.
Oh, and one thing I want to point out about this is you can just trust the signs. You don't have to worry about your own positive or negative here. If T is positive, the stress is positive. If T is negative, the stress is negative. Okay, so we're going to do a cut along the green line. So an FBD, free body diagram, looks like this. We're leaving off this part of the beam. And we have 8,000 this way. Over here we have 2,000. And we don't make it all the way to the end, so the only other thing we have is a tension. You could also put in the, shear force and bending moment and torque, but those are all going to be 0. So I'm just leaving them off here. And so Newton's second law says the x component says negative 8,000 plus 2,000 plus t is equal to 0. So t is equal to positive 6,000. So that's the internal tension at that point. And so the XX stress due to tension is equal to positive 6,000 divided by 0.001. And that's 6 times 10 to the 6 pascals. That's the only thing that's affected by this internal tension. That's the only element that's affected. And so our stress tensor due to tension is 6 times 10 to the 6, zeros everywhere else. What if I added a bunch of other junk here, like a couple at each end and a torque at each end, a vertical force in the middle? What would change about calculating the stress tensor due to tension? Nothing. We would deal with those separately and then at the end add them up, but this would still be the analysis we would do for the tension part. Okay, so that's the easier one. The next one is the stress due to the bending moment. And for all of the rest of these, we need to be careful about the requirements for these formulas to work. So careful. Does the beam meet these requirements?
You need meat in there because you have
Does
to
the-
deem these requirements.
I don't find that funny. Okay, so here's the requirements. So here's the column of examples of things we can do the calculations for, and here's the ones we can't do. Okay, so the first requirement is the beam has to be straight or close to straight. So we can do beams that look like that from the side, but we can't use this analysis for, something like that with a drastic curve in it. We can't think of that as a beam for this analysis. The second requirement is it has to be prismatic. So we can do a beam like this, but we couldn't do one like, this is hard to draw. The cross section has to stay the same the whole way down. The third one, maybe the one that comes up the most often, is the cross-section has to be symmetric about the vertical axis, or what for us is always going to be the y-axis. Okay, so we can do pretty complicated cross sections. We could do something like that because it's symmetric about a vertical axis. That means that this is our bending axis. But we can't do something like bending it this way. We could bend it, we could do calculations where we were bending it the other way. You know what I mean? Because then we'd think of this red one as our vertical axis, our y-axis, and then it would be fine. But if this is our bending axis,
that's the bending axis. Like it bends kind of like it bends around.
yeah, so picture that shape coming out of the board, okay? And picture someone standing on it, on the end of it, like a meter out, a couple of meters out from the board. And the bending that would happen from that motion is what we're looking at. So,
Kind of bend like just coming out of the board like this or something.
yeah, so that's the bending that we're analyzing, is it bending down towards the floor. This one, if we were doing an analysis where it was bending towards the wall, that would be fine, because we would do our calculation with it flipped this way, and then it would be bending towards the floor. But we can't do bending towards the floor in that shape because it's not symmetric about the y-axis. Any other questions about that?
Why is that number 3?
Y is number 3. I don't remember.
I'll Google it later.
Okay. Yeah, yeah, I'm sure there's a way to derive it, but I don't remember how to do it. Any other questions? So, Howard, what happens to create these stresses in bending? So understanding the stresses due to bending. So if you take this beam and bend it, obviously this is a large deformation, so we're not going to do deformations that big, but and this is your coordinate system. Let's think about 3 different lines. So let's say the red one, actually let's put the red in the middle because that's the bending axis. And let's put blue on the bottom and green on the top. Then after you bend it, where's the red axis going to be on this bent shape? It's going to be curved. It's still going to be in the middle. I don't know if you thought maybe it would move to the far extreme or be ejected from the shape or something, but that won't happen. And the blue will be like this. And the green will be like this. That's not green. Okay, so what happens to the length? What?
Thank you so much.
What happens to the length of these 3 lines? That's the question, the new question.
Green gets shorter, blue gets longer.
Yeah, perfect. Exactly. That is the key, the 3 key things. Green gets shorter. Blue gets longer. And red stays the same length. And so, even though it might seem a little weird at first that this is the case, the stresses that are developed by a bending moment are XX stresses. They're X normal stresses. Like this green one is in X compression, because it's just getting shorter along the x-axis. The blue one is in XX tension because it's getting longer. The red one doesn't feel any stress at all because it's staying exactly the same length. So we know two things. The stress due to bending has only an x normal element, only one non-zero element. And we know that the XX stress due to bending is equal to 0 somewhere in the middle. Did I say two things? Let's do it like four. Third, the XX stress is negative as you move towards the center of curvature. You know what I mean by that? Can you picture that? Yeah, the green one in this case. But, you could bend it the other way and then it would be opposite. So the center of curvature is the middle of that. So it bends into like a circular shape with some gigantic radius if it's a small deformation. But if you're moving from that center line toward the center of that circular shape, then the XX stress is negative. And fourth, it's positive if you move away from the center of curvature. So notice that creates this difference. This is a new thing that didn't happen with the stress due to tension. When you're dealing with bending moments, the stress due to bending varies along a single cross section. We didn't see that. That didn't happen with the stress due to tension. You see what I mean? Can you picture that? No. You can, but you won't. Okay. Okay, so we need two mathematical definitions before we can come up with the formula for how to calculate this stress. Two new mathematical definitions. The first one is the neutral axis. And it is a horizontal line through the centroid of the cross-section. Parallel to the z-axis. Okay, so if this is the beam, the centroid of the cross-section is here. The neutral and our coordinate system has the x-axis along the beam's long axis. This is the coordinate system that we've been using for beams this whole time. The y-axis points up. That's that vertical axis. And the z-axis points this way. Then the neutral axis is this green axis. Now, if you extend that neutral axis along the whole length of the beam, you get a plane. Can you see that? And that plane doesn't change length under deformation. It stays the same length in the x direction as the beam deforms. Okay, so what that's saying is this red line that under deformation doesn't change length, that is a side view of the neutral axis. I didn't. Sorry. Okay. Okay, so we're not going to do the other one today. We'll do it on Monday. But the next one is perfect way to end the class. The second mathematical definition that we're going to need is the areal or area moment of inertia about an axis. And that's why when you build up a bulging sheath of bone around a fracture, that bone, that bulged out part is less prone to breaking than the streamlined part of the bone, because this area moment of inertia increases. And for the people taking dynamics, this is the one that I said to be careful of. This is the one that we call capital I sub A, and it has a parallel axis theorem and all the same things that the mass moment of inertia has, but it's a totally different thing.